Hello, I'm Haorian Mo from Sun Yat-sen University. I will talk about our work on vector line art generation. Vector line art plays an important role in graphic design, such as engineering design, 2D animation, and 3D printing. Vector image is widely used because of its unique advantages. First, vector image is a resolution-independent representation. Second, compared with raster images, vector images allow more flexible editing. Although vector line drawing is commonly used, it is tedious to manually create. Vectorization approaches are able to produce vector images from raster drawings directly. However, they tend to take a long time for computation and have difficulties in processing sketches with rough textures. In most cases, it is not clean line drawings, but rough sketches that need to be cleaned up and vectorized. Rough sketch simplification methods are able to generate raster clean line drawings, but they require post-processing to convert the result to a vector line image. Next, I will introduce our work. We propose a general framework for vector line drawing generation. The framework works with a wide variety of images, such as clean line drawings, rough sketches, and photographs. Our framework learns to produce vector line art without requiring vector data for training. In order to process images of arbitrary resolution, we propose a dynamic window mechanism. We also introduce a stroke regularization mechanism to control the simplicity of the output vector images. Our framework models a virtual pen surrounded by a dynamic window and generates vector strokes by drawing with the virtual pen. The drawing process consists of four main phases. First, patches from the input image and canvas are cropped based on the window. Then, based on the patches, the stroke generator produces the vector parameters. Next, the stroke parameters are approximated into a stroke image through differentiable rendering. Finally, the stroke image is pasted to the last canvas based on the window. Afterwards, the window moves as drawing the stroke. The framework is based on a recurrent model. It draws the next stroke based on the previous canvas till the end of drawing. The model is able to move the pen around by sliding to a new position without drawing. Our model also learns to choose the best window size. For example, when there is no undrawn pixel inside the window, the model is able to enlarge the window to find undrawn pixels and slide there. Afterwards, it shrinks the window and restarts drawing. In the cropping and pasting phases, one challenge is that the position and window size are floating numbers instead of discrete values. Solution with quantization leads to misalignment and non-differentiability. To overcome these issues, we propose aligned cropping and differentiable pasting. Our framework doesn't need vector data for training. This is achieved by differentiable rendering technique. The output vector parameters are approximated into a raster image through a neural renderer. Then this image is compared to the target image to form a raster loss. This enables raster-only supervision. Another feature of our approach is the stroke regularization mechanism. In the vector output, there are short segments and overlap strokes. With our stroke regularization mechanism, the model is able to use fewer strokes to represent a line drawing. Our framework works on vectorization tasks. We compare with two representative vectorization methods. We can see that fidelity versus simplicity fails to draw isolated strokes. Polyvectorization misses small strokes around complex junctions. The computation time under the figures shows our approach is much faster. Our approach can also be applied to rough sketch simplification tasks. In the results of baseline methods, we can see no completion and artifacts. Our framework also works with photographs like the facial images. Compared with baseline methods, our approach generates comparable facial sketches. We have released the code and the trained models. Thank you.